Ordinary sand is a fascinating material. On the one hand, in many parts of the world, serious ecological and economic problems are caused by sand drift and desertification, that is, the generation of new desert-like areas through the influence of the forces of nature or man. In fact, about 1/4 of the land surface of the Earth is covered by desert, and this area is constantly increasing. Denmark is one place where sand drift is of considerable concern in relation to both agriculture and preservation of the coastline. Heavy storms engendering sand drifts which causes serious damage to Danish crops are by no means rare. On the other hand, sand is a material with remarkable physical properties, resulting, for instance, in the beautiful regular dune forms which are seen in the main desert areas of the world. In Denmark, there are only smaller regular features of sand surfaces, such as ripple patterns and shield dunes. A proper understanding of the physical laws behind these phenomena is of great interest, both for nature preservation and from the viewpoint of basic research. As a scientific field, the physics of blown sands has been founded largely by one man, Ralph Alger Bagnold, whose book from 1941, The Physics of Blown Sands and Desert Dunes, is still a main work in the field. Born in England in 1896 and a Fellow of the Royal Society of London since 1945, Dr. Bagnold has enjoyed a long and very extraordinary life. After his work on blown sands, he began to study the related questions of transport and sedimentation of silt, sand and gravel in flowing water, making a number of major scientific contributions to that field as well. However, he has never held a position at a university or other institution of research or higher education, so that his studies have been largely a private enterprise. Even more remarkably, Ralph Bagnold had an equally illustrious career in the British Army. He served in both world wars, ultimately with the rank of brigadier, and it was he who conceived, raised and commanded the small motorized long-range desert group, which played an important role before and during the war in North Africa. Between the two wars, he had acquired an intimate knowledge of the Libyan desert, a vast sea of sand in which he was able to navigate by means of a simple sun compass of his own invention, very much like a ship on the ocean. Among the places where the physics of blown sands is being studied is the Faculty of Science in the University of Aarhus. Here, a research group of geologists and mathematical statisticians is making investigations which in many ways continue the pioneering work of Dr. Bagnold. These investigations comprise both field observations and wind tunnel experiments, as well as theoretical work of a mathematical character. In 1978, Brigadier Bagnold was awarded an honorary doctoral degree from the faculty in connection with the 50th anniversary of the University of Aarhus. Dr. Bagnold, your rank of brigadier and your title of Doctor of Science is a very unusual combination. Which was your first love, the army or scientific research?
Oh, the army first. My father was a colonel in the Royal Engineers, and I thought nothing better than to join the Royal Engineers as my father had. But when I was a boy, long before the time came for me to join the army, A neighbour of ours had a large electrical laboratory, private laboratory, which he had inherited from his father. And I used to go and play with instruments, now very old-fashioned instruments, of course. And I got a great interest in science from those visits to our friend's laboratory.
Nevertheless, there was no doubt in your mind that you simply had to go into the army.
Oh yes, that was the...
that was the atmosphere at
the
home.
Atmosphere, yes,
and your father's influence, and,
yes.
and perhaps even longer back.
Well, yes, his father had been in the army, in the Indian army.
He served in India?
Yes.
Where did your father serve?
In Egypt, South Africa, and in the West Indies.
Was in the famous campaign in Egypt in the 80s?
Yes, he was in charge of communications, telegraph, which was then a new thing. In the expedition, the 100 expedition, which was organized to try and relieve General Gordon, who was besieged in Khartoum.
So even in your boyhood there was, I suppose, much talk of Egypt?
There was, certainly, yes.
Yes. Now, when did you go into the army yourself?
I passed the exam into the Royal Engineers on August 1914, almost the same month as war was declared, the First War.
So you made the Great War also?
I went to France in the spring of 1915. I was in France and Belgium for the rest of the war.
In the trenches?
In the trenches for the first 2 years, and afterwards in signal communications.
Unfortunately, you were one of those who returned. What did you do after the war?
Well, first of all, the army had too many, as one would expect, the army had too many officers just after the war. And they encouraged those who would want to go to a university for 2 years. And I took advantage of that, encouraged by the fact that my colonel during the war was a professor of astronomy at Cambridge University. And it was he who suggested that I should go to...
Who was he, by the way?
Colonel Stratton.
Stratton, yeah.
It was he who suggested that I should go to Cambridge, to his college. And I found that he was my tutor.
Which college was that?
Condell and Keys.
Condell and Keys. So you spent some years there?
2 years.
2 years only. And came out with a degree?
Yes.
In which subject?
In engineering.
In engineering, yeah. That must have been a very different life from...
Well, it was the best,
previous one.
the happiest time I ever had in my life.
Ever?
After graduating from Cambridge University, Ralph Bagnold was stationed with the British Army in Egypt, and there he began, with some friends, to explore the deserts east and west of the Nile, in privately owned 4T motor cars. He developed great skills and techniques for desert travel, and wrote a fascinating book on his experiences called Libyan Sands, describing, among other things, the old Siva oasis. Gradually, his curiosity was awakened as to what were the physical laws that determine some of the remarkable properties of sand, such as the strikingly regular dune shapes.
Yes, indeed. The dune shapes were so much simpler than what one sees along coasts where there's been rain. If you get into the real waterless desert where there's no vegetation at all, one finds simple forms repeating themselves over a large area of country. If the wind is always more or less in one direction, one has the beautiful isolated forms of the Balkans, like crescents, like crescent buns, moving forwards with their arms outstretched in the direction of motion. And one has another kind of dune, which is a long, continuous chain of sand summits, almost in a straight line for many hundreds of kilometers.
One of the approaches by which Bagnold hoped to explain the occurrence of such dune forms and also the phenomenon of the so-called singing sands was a study of the distributions of the various sizes of the sand grains.
Yes, I took an interest in the sizes of the sand grains, hoping that the extraordinary, rather rare effect of a sand dune, which suddenly makes an extremely loud noise like an aero engine, without warning at all. And occasionally you find dunes which will do that, but mostly you can't get the noise out of them at all. I hoped that by analyzing these sand sizes, the distribution of size, that one might get some line on whether or not the noise was due to some peculiar distribution of grain sizes. So I analyzed a great many samples for the size distribution.
To determine such size distributions, samples are collected from the sand deposit to be studied, such as a particular sand dune, and the samples are brought into the laboratory. Each sample is separated into size fractions by sieving the sample through a series of sieves of decreasing mesh sizes. Each sieve is carefully emptied, and the subsample of grains thus obtained is weighed on a high-precision weight. If we place the subsamples from the various sieves consecutively on a table, we have a direct physical representation of the size distribution. A graphical representation is obtained from this by plotting rectangles side by side, each rectangle corresponding to a subsample, and the area of the rectangle being proportional to the weight of the subsample of sand grains. More concisely, we might just plot the middle top points of the rectangles. Bagnold came upon the idea that a more informative picture of the size distribution would emerge by plotting the diagram of rectangles or the top points in double logarithmic scales.
And it appeared that on log paper, all the analyses of sand which I did showed that the distribution picture was unlike what one would expect from the accepted probability distribution. In fact, it looked more like hyperbola, that is, with straight line arms going away on each side, so the coarse, extremely coarse sizes and the extremely fine sizes.
For the further analysis and applications of Bagnold's idea, it was essential to formulate the idea in mathematical terms. It turned out not only that the hyperbolic distribution suggested by Bagnold could be fully expressed by reference to a type of function well known from applied mathematics, but, rather surprisingly, that the same mathematical formula described a considerable number of empirical distributions from quite different fields of observation. For instance, distributions of contents of gold per ore, of accelerations in a turbulent atmospheric field, of lengths of beans, of personal incomes in Australia, besides size distributions of sand deposited by wind or by water. Even more unexpected, the three-dimensional version of the hyperbolic distribution occurs in Einsteinian physics as a distribution of the momentum vector of a single particle in an ideal gas, as seen by an observer who moves at a constant speed in relation to the gas. for the description and understanding of how the wind transports and sorts the sand. The first thing to note is that there are three distinct modes of particle transport related to grain size. The predominant mode in terms of material transported is saltation. In this mode, the particles are lifted almost vertically into the air and follow trajectories of a typical kind, often performing a series of saltation jumps in succession. The largest particles moving do so by creeping. That is, they roll along the surface of the sand bed, being set in motion by the impact of descending saltating grains. The finest grains are lifted into the air and carried away in the wind by suspension. The construction of a mathematical physical model for the transport process is the main aim of the research currently being carried out at the Faculty of Science. The basis of such a model is now available, but to test the theory proposed and to develop the model further, extensive experiments are required. Many of these experiments are performed in a 15-meter long wind tunnel. In one type of experiment, a stack of plastic chambers is used to trap the saltating grains at various heights above the sand surface. The mass of grains in each chamber decreases exponentially with height. Analysis of the size distributions in the various chambers is an important part of the development of the transport model. A related but in significant ways different field of investigation is that of sediment transport in water streams. After the Second World War, Bagnold turned his attention to that field, and through the 1950s and 60s he published a number of papers on alluvial sediment transport, which are of an importance comparable to that of his work on aeolian sediment transport. In the last decennium, from about 1975, Bagnold's theory of blown sand has found new applications in the studies of our neighboring planets through the use of space vehicles. His investigations from the 1930s have turned out to be of crucial importance for the understanding of conditions, in particular on Mars. Indeed, the kind of ground that Bagnold and his long-range desert group sometimes had to struggle with is strikingly similar to the Martian surface at the location where the spacecraft Viking 1 landed, as appears from this photograph taken on August 3, 1976 by a camera on board the Viking lander and transmitted back to Earth.